When it comes to first understanding electron configurations, it's easiest to think about the periodic table as a system of blocks, kind of like a floor plan. Let's first start off with the S block. The S block is this region that is 2 columns wide. The S block has a spherical shape, and it starts off with 1, and that is right here. There's something that is important to note about the S block. Hydrogen is here, and helium belongs right next to it. So helium is an S block element, which means that it does not belong here for the purposes of electron configurations and electronic structure. Since the S block begins with 1, the first row is 1s. The second row is 2s, followed by 3s, 4s, 5s, 6s, and 7s. There is no 8s as of right now. The next block is the P block, which is outlined here. The P block has a dumbbell shape, and it begins with 2. So there is no 1p. It immediately starts with the 2p row. 2p, 3p, 4p, 5p, 6p, and 7p. For the S block and the P block, the integer, the number in front of the S, the P, or later the D and the F, for the S and the P block only, those integers do correspond with the row, more technically known as the period. There's another block called the D block, which is outlined here. Interestingly, the D block begins with a 3, but it is not on the third period of the periodic table. The D block has mostly a cloverleaf shape, and there is a 5th shape that is not quite a cloverleaf. And if you want to look up some of the other shapes of the D and the F block, they do get a little weird, and there are some mathematical functions that correspond to them if you wanted to delve into that depth. The last block of the periodic table would be the F block, outlined here. You have to be careful because although they are called the lanthanides and the actinides, lanthanum, which is here, is actually a D block element, and actinium, which is here, is actually a D block element as well. So on some periodic tables, you will see that this bottom set is 15 wide, but it's really 14 wide, and occasionally lanthanum and actinium are added to that row, but they are actually D block elements. With this being the F block, it has shapes that are too complicated to draw, and most of the time when you do electron configurations, you might identify F block elements, but in a standard high school chemistry course, and even in college and AP chemistry courses, rarely will you have to give configurations for F block elements. But the same procedure applies for F block elements as it does for the other ones. They are just a little lengthier to get to, even with the shortcut. The F block starts off with the number 4. And it would have then two types. You have 4F and 5F. For this next part, you should have a periodic table handy, but if you don't, then hopefully have a little bit of it memorized. Suppose you have an electron configuration that is 1s2, 2s1. How would you identify which element that is? Some students have figured out some fast tricks that work some of the time, but I will teach you how to do it from scratch. First, understand that this coefficient here, every large number that touches the ground, deals with which level of that block it is. For example, 1s1 or 1s2 both refer to the 1s level of the S block. And as you go down, it can go from 1s to 2s to 3s, 4s, 5s, 6s, and 7s. As you leave the 1s block and continue through the periodic table, you hit the 2s block. If you leave the 2s block, you actually enter the 2p block. Continuing, you hit the 3s block, jump back across to the 3p block. Continuing out of the 3p block, you enter the 4s block. Then you enter 3d, then 4p, then 5s, then 4d, then 5p, and so on. Don't be weirded out by the fact that the coefficient changes from a 4 to a 3 as you leave the S to the D block. When students first learn this, they're often weirded out by the apparent complexity of it, but identifying elements based on their electron configurations is easy. 1s2, 2s1 is the electron configuration for a neutral atom that would be, let's count it out. 1s1 would be hydrogen. 1s2 would be helium. There is no 1s3, and here's why. The maximum superscript, which would be this number here, any high number, is 2 for S, because the S block is 2 wide. So you cannot have 1s3 or 1s4. The maximum superscript for something S something is 2. Knowing this, what do you think the maximum superscript is for the P block? The P block has a maximum superscript of 6 because it is 6 columns or groups wide. Likewise, the maximum superscript for the D block is 10. And the maximum superscript for the F block is 14. Continuing on with our first example, 1s1 is hydrogen, 1s2 is helium. Since there is no 1s3, we have to go to the next level down. 2s1 would be lithium. The superscript tells you how far into that particular level of that block you should go. Lithium is the first element in the 2s row. Therefore, it has a 1. Let's identify 1s2, 2s2, 2p5. Starting off with hydrogen, because that is what the Aufbau principle says to do. 1s1 would be hydrogen. 1s2 would be helium. There is no 1s3, so continuing down, 2s1, 2s2, we are out of things in the 2s part, so we have to jump across to p. And it is evident in our configuration that that is what's happening. Remember that P starts off with 2. 2p1, 2p2, 2p3, 2p4, 2p5. We've counted all the way from 1s1 to 1s2, 2s2, 2p5. So this electron configuration represents fluorine. A neutral element, or a neutral atom of fluorine. Right next to fluorine, we have neon. Could you guess or figure out what the electron configuration would be for a neutral neon? Pause the video and think about it. If you said 1s2, 2s2, 2p6 for neon, then you would be correct, because neon is the 6th element into the 2p row. Let's figure out what 1s2, 2s2, 2p6, 3s2 is. 1s2 covers these two, 2s2 covers these two, jump across, and you get 2p6, which means that the entire 2p row is filled up. And then you have 3s2, which stops us off right here. This destination is magnesium. We're going to kick it up a notch and see if we can determine the electron configuration for an element rather than finding out what element something is from the neutral electron configuration. On your screen, if you look closely, the very end of the D block should now have zinc on it, because that is where zinc is located. Let's see if we can count up to where zinc would be for its electron configuration. From our last example, we already have it filled in, or counted up, to 3s2. We have 1s2, 2s2, 2p6, 3s2, and this is where we stopped because that is where magnesium is. But as you can see, zinc is farther down than magnesium. So let's jump across and continue. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. That is certainly one stop, one of our blocks, or one of our turns, so to speak. Continuing, we see that after we fill up the 3p set, we go down to 4s, 4s1, 4s2. Now we enter the 3D region. It begins with 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. As you can see, the blocks make themselves pretty evident once you understand what's going on, and you can trace them out with your finger. You will go back and forth between the S and the P blocks before you get to the D block if you were to find an element with an electron configuration that is beyond calcium. Now, let's figure out the electron configuration for selenium, starting off with hydrogen, as we typically do, which is 1s1. We've got 1s1, 1s2, so that gives us 1s2. We are going to have the 2s2 set filled up as well. Now we jump across to the P block, which begins with a 2, and of course we're going to go all the way through in our quest to get to selenium, giving us 2p6. Then we go and fill up the 3s area. And that would make it have 3s2. Jump back across and fill up the entire 3p line, making it 3p6. After 3p6, you've got 4s2, and after the 4s2 is filled up, then you jump into the 3d. And you're going to go all the way through from 3d1 to 3d10. And as you saw, that was zinc. However, we are beyond zinc now, and we're going to have to jump into not the 2p, not the 3p, but now the 4p. And the superscript for that 4p will be how far into the 4p we are. And we are going to be 1, 2, 3, 4. And this is where we're going to stop, making it 4p4. By this point, you're thinking, wow, this can take a long time and a lot of ink if I have to write out the electron configuration for things that are far down. However, there is a shortcut that I'm about to show you just as an introduction. I've cleaned up the periodic table a little to make it easier to read, and I also, if you noticed, moved helium back into the noble gas family, and that is for a particular reason when it comes to thinking about the shorthand formula for electron configurations. Helium will remain 1s2, that is why it is red, but it is best understood to remain in the noble gas family for this. Helium is a noble gas, the smallest of them all, with an electron configuration of 1s2. This 1s2 refers simply to the helium. But let's think about what other noble gases are in this family. We have neon, argon, krypton, xenon, radon, and the most recently discovered or created noble gas, oganesson, which may or may not be a gas. The chemistry is not easy to experiment with because it is so short-lived. Thinking about where selenium is, we know that selenium has an electron configuration that starts with 1s2 and goes all the way up to 4p4. But that's a lot to write. So instead of writing out all of that, what you can do, if you are permitted to use the shorthand formula or asked to use the shorthand formula, is find the most recent noble gas. When I say the most recent noble gas, what that means is find the noble gas that has an atomic number less than the element of interest, such as selenium in this case, and not greater than. I don't want to say the closest noble gas because it would appear that krypton is the closest noble gas. When I say the most recent noble gas, that would actually mean argon. Let's figure out first what argon's electron configuration is, which would have to be somewhere inside of selenium's full neutral electron configuration. Argon would start with 1s2, 2s2, 2p6, 3s2, 3p6, which means that argon is everything that is enclosed in this purple box. So rather than writing out all of that, the shorthand would be argon in square brackets, followed by everything that is not enclosed in the purple box, which would be everything that is beyond argon. So it would be 4s2, 3d10, 4p4. This would be called the shorthand configuration. The shorthand electron configuration, which always uses a noble gas only inside square brackets, and that noble gas has to be less than, in terms of atomic number, or before the element of interest. You cannot abbreviate a noble gas's electron configuration with itself. For example, if someone asked you for the electron configuration of xenon, you could not just say, well, it's xenon. You cannot abbreviate a noble gas with itself, but you could abbreviate the electron configuration of xenon using krypton, which is the most recent noble gas before it, and then all the stuff that comes after it, starting off with 1s, 2s, 3s, 4s, the 5s2. This video is not going to get into electron configuration exceptions, which usually happen in the D block. This video is going to end with some practice, both in identifying elements from a given electron configuration and creating some shorthand electron configurations using the noble gas. If you want to practice these on your own, pause the video and see if you can figure them out. For the first section, I'm going to let you in on a secret that some of you may have already figured out. When it comes to identifying elements from their electron configurations, the easiest, quickest thing to do, if it's given either full or shorthand, is to look at the very last section. And if you remember where the blocks are and what numbers they start with, it shouldn't be that hard to figure out where it is. Remember, S starts with 1, P starts with 2, D starts with 3, and F starts with 4. If you're looking for something that starts with 1s blah 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 and goes all the way to 3p1, you know that you're not here. You are somewhere in the 3p region, and this 1 lets you know that you are only 1 deep into that 3p line, meaning that 1s2, 2s2, 2p6, 3s2, 3p1 is aluminum. Another trick, if you count up all the superscripts and add them up, 2 plus 2 plus 6 plus 2 plus 1, and it's referring to a neutral element without an ionic charge, then the sum of the superscripts should equal the atomic number. 2 plus 2 plus 6 plus 2 plus 1 is 13, which is the atomic number for aluminum, because aluminum would have 13 electrons if it's neutral, because it has 13 protons. That trick I just told you about counting the superscripts does not work if it's in a shorthand formula, because the only superscript in the second example is a 1. So you have to think about where it truly is. What you can think about is that neon 3s1 is some element that is not neon, it is beyond neon, and it resides in the 3s1 block. It is only 1 deep into the 3s1. So 1s2 would be hydrogen helium, 2s1 and then 2s2 would be lithium beryllium. We are talking about sodium, because sodium is in the third level of S, and it's only 1 deep. For the third example, find 4d1. 4d1 is not in the 3d, it is in the 4d, and it is 1 deep, making it yttrium. Be careful with the D block, as there are some electron configuration exceptions. In creating the shorthand electron configurations using noble gases, we should first find where the element is on the periodic table. Manganese is here. And as you can see, it is 5 elements in to the 3D section. But that is not the entire electron configuration. If you're going to do the shorthand electron configuration without all the extra writing, you still have to figure out what noble gas to use. The noble gas that we are going to use is the most recent noble gas, which is the noble gas that has an atomic number less than manganese, but closest to it. And that would be argon. As you can see, argon ends at the 3p6 region. That means that we would pick up at 4s2, which would be this section here. Then we jump into the 3D. I'm going to make sure my colors are consistent. 3D, and we already can see that it is 1, 2, 3, 4, 5 into that section. And that would be the shorthand configuration for manganese. Chlorine is right here. And although argon is a closer noble gas, it is beyond chlorine's electron configuration. Therefore, we would actually use neon. Neon, just like every noble gas except for helium, ends in something something P6. Neon ends in 2p6 because it resides at the end of the 2p row. And what we would find if we pick up after the 2p6 is 3s2, which covers these, and then you jump across to the p section and go 5 deep into the 3p row. And it would make sense that it is neon 3s2 3p5. The element barium is way down in the S block, and to write out the full electron configuration would take a little bit of time, but you can totally do it. To figure out the shorthand electron configuration, find the most recent noble gas, which would be xenon. What changes since xenon, that is, what is not covered in xenon's implicit electron configuration, is simply a 6s2, 1s2, 2s2, 3s2, 4s2, 5s2, and then 6s2 leads us right to barium. If, for example, we were doing cesium, it would end at 6s1. That is all there is for this excessively long video, and hopefully you learned something about electron configurations and how to use the periodic table to figure out both shorthand and longhand configurations.